Hey pal, how you doing? This is Tony Lockwood. I'm at CAASE 18 and digital engineering, and Nathans are the co-hosts of this conference. Now, I have a very interesting discussion coming up here, and I would like to turn it over to you and say, please tell us your name, your title, the company you work for, a little bit about the products that you make.
Yeah, thank you, Tony, for the invitation for the interview. I'm Flavio Souza, the president and CTO of MultiMechanics. Our main mission in the company is to accelerate innovation and adoption of new materials through predictive simulation by integrating the material engineering to the manufacturing part design. And we do that by developing software solutions that go into the micro-scale level and account for all the microstructure design variables.
Now, you got this material testing, and you work with some of the big analysis simulation products, Abacus, ANSYS, for example. Materials is pretty hot, all over. Whether you're talking aerospace, 3D engineering, light weighting, everything, and somebody's always coming up with something, but it's not an easy thing to deal with. How are you making it easy for engineers to deal with it in terms of their simulation? Because it has its own language and everything associated with it.
So one of the big challenges with advanced materials is that now we have the freedom to combine different materials in different ways. And the challenge is how do you predict those properties from those materials? You don't want to go to the lab and experimentally test every type and every possible combination of materials. So what we're doing is we develop a platform that is enabling engineers and material scientists to do that virtually. And now material developers have the freedom to account for all those different types of combinations, different types of materials, how they interact. They're able to understand very well how their material behave, and now think about innovative ideas where they can now come up with new materials or new ways to combine existing materials to achieve some specific performance requirements.
Now, are the things like the increased hardware power, graphics, high performance computing and whatnot, is that really helping drive you along in some ways?
Yes, it's a very good question. It's one of the big challenges we have been facing over the years as we develop the solution. So our approach was we first made sure that we have an accurate methodology. And the methodology would require you to have a different individual material microstructural models for each integration point in your final element model. And we have a very strong coupling between the two models. So you have an airplane wing where you're using either one of our partner solutions to model the airplane wing or our own standalone solution. And on the microstructure level, we are solving using MultiMech the microstructure model. It's really bringing the final element approach to the microstructure level. Now you can imagine if you have 100,000 integration points, you have 100,000 new microstructure model. That's big simulation.
That is.
So what we've done to overcome that, in addition to high performance computing, was we developed new mathematical formulation, a new data compression algorithm that combined together, they give us up to 1,000x gain. In average, it's between 100 times and 400 times. So we're really bringing simulation that used to take 24 hours and 55 gigabyte memory to run in a laptop computer. Now only takes 12 minutes and 2 gigabyte memory. And with the same level of accuracy, which is one of the biggest drivers in our company.
Yeah, you always want it accurate, and more accurate.
Yes.
The
Yes.
better. The whole the buzzword is democratization. Is that applicable to the type of analysis simulations you do, or is it still sort of highly specialist
You can think of it as a specialized solution, but we do face democratization problems as well. And one of the big ones we have is on the material properties, on the material data. Typically, you can easily find elastic properties for individual materials like the fiber and resin. We're talking about composite materials. But really, those materials don't behave like that. They have, especially the resin,
Right.
it's highly nonlinear thermoviscoelastic material. And one of the things we're doing is we're working closely with our clients, especially Solvay, who is a material developer, to properly characterize those materials and make that information available to our clients. In the sense that our end users won't have to do that work. And we're going to provide them ready-to-go microstructural models to plug into their part designs.
Now, how do you keep up with the materials are really changing dramatically, and then there's build your own material, like create your own that never existed before. That you know, that's a tough problem.
Yeah.
You guys are working on. That's tough stuff. How do you teach people how to do that? Do you go into a company and train them on this? It's you know what I'm saying.
So we tend to focus on fundamental principles and try to develop models that you won't have to redo the work. So basically, if you're coming from the ground up approach where you characterize your individual materials, but any geometric consideration or any type of arrangement or orientation of fibers, it all comes from the model. It's a response that you get from your simulation. It's not something that you need to characterize or anything you need to go to the lab and measure. So if you can do that very well, you only need to do a specific experiment to characterize individual constituents and not the full coupon or anything. And including manufacturing variability can all be predicted as well. And when you build a composite part and you have clustering of fibers or you have resin pockets, that can all be predictable. You don't have to make up many different coupon tests and run in the lab to get the statistical variation. You can get that answer from simulation.
Are your customers facing any particular challenges or want particular features out of you to help them meet those challenges?
Yeah, the overarching problem our customers are facing is reduction of physical testing. And the ways we help them to do it is, one, we try to come from basic principles where you're only characterizing the individual constituents. But it also comes to accurate failure prediction at the microstructural level, like being able to account for fiber break, matrix cracking, fiber resin debonding, as well as curing capabilities, where you can really model the curing of the resin and predict the residual stresses as a result of the mismatching coefficient of thermal expansion and so forth.
Now, let's ask you to do this. I would like you to tell us your website so that people can go to you and get see some more what's going on. It's an interesting website you have, by the way.
Thank you. Our website is www.multimechanics.com.
Very good.
And we have a wealth of information there, and we're going to keep adding more content as we go.
Yeah, very good. Yeah, it's good stuff, folks. All right, I will have that web address available for you. Just write the DE editors, and I'll be happy to send it. If you have trouble with your manual word processor, scribbling it down during the course of this discussion. I want to thank you very much, Flavio, for
thank
your
you, Tom.
time, and thank you, pal. And